What did we talk about last time? I don't want to remind me. Oh yeah, we did constraints and stuff. Uh, so yeah, last time we talked about specifically minimization with equality constraints, right? So that involves like Lagrange multipliers and stuff like that. And then we kind of finished off like doing a little example with like a pretty simple kind of quadratic equality constraint where you're trying to ride along this like parabolic kind of surface, right? And we saw kind of at the end of that there were some issues, right? And so we're going to circle back on that a little bit later today. But I think the main topic for today is, so last time we kind of did equality constraints. Today we're going to venture into inequality constraints. Talk a little bit about that. We should get through that. And then we'll start to like talk then about how to fix these like last few little lurking demons, if you will, right? Like these kind of issues with getting stuck or overshooting or whatever in the constrained setting, right? So today, basically, inequality constraints is the name of the game. There'll be like a few different things here and there. So any questions about any of that? What we're doing, what we did? Okay, excellent. So let's get into it then. Get rid of this weird cord thing that's in my way. Okay, so to kind of lay the stage, we kind of like left off in this spot last time, and I just kind of threw some stuff at you that we didn't really talk about in any depth. So we're going to do that again and then dig in and tell you how to actually deal with this stuff. So we're talking about inequality constrained minimization and kind of the generic setup for this, which we just sort of threw at you last time, is kind of here's like the prototypical example, right? So minimize some function f of x subject to some constraint c of x that's greater than equal to 0 or non-negative, right? So you'll see this a bunch of different ways, right? You'll see that sometimes people will write the inequality the other way and make it less than equal. That's fine. It's the same thing. It's just a minus sign on the C, right? So kind of either way you want to do it. You'll see a few variations on this kind of standard theme. Also, in general, you'll see it subject to equalities and inequalities in general, right? We already talked about how to do equalities last time. And so today we're going to focus on just the inequality stuff. And at the end, like putting those together is trivial. You literally just combine both techniques and stack everything. So in general, you might have like a C of x non-negative and a d of x equal to 0. For the equal to 0 part, you do exactly what we did last time with some Lagrange multiplier stuff. And you just stack that along with what we're going to do today for the inequality. So you can just put them together, no big deal. Okay, so having said that, let's write down what we finished off last time was these so-called KKT conditions. And these are sort of the real KKT conditions. And in general, you can have both the equality and inequality stuff smushed together, just stack it all. So we'll write these down and then kind of draw the picture again and explain kind of some of this stuff. So here's this one is called stationarity. And then we've got the constraint being satisfied. This one is called primal feasibility, meaning the primal variable, the x, is feasible with respect to the constraints, obeys the constraints, right? Then we've got a constraint on the multiplier being positive. This is called dual feasibility. Basically just saying the dual variable or Lagrange multiplier has to obey the constraints. And in this case, they have to be positive, right? And then we've got this last one that says lambda times c of x has to equal 0. This is called complementarity or complementary slackness. Some variation on that theme. I'll, just call it complementarity. It's shorter. Cool. So, and we talked about last time. So to be clear, this little weird symbol, right? The circle with the dot in the middle. Anyone know what that's called? Mhm. Someone said something. So yeah, this is an element-wise product of two vectors. So this just says if I have two vectors the same size, you're going to go across and multiply every element of the vector, and the output's another vector. So you can call this element-wise product. There's also the other name for this is the Hadamard product. So just FYI, right? And you'll see these things written down slightly differently sometimes. So this one is the one we're going to stick with because it's actually the one that's algorithmically going to show up in the code for us when we get into this. You'll also, though, see it written as lambda transpose C equals 0. So that's a dot product, right? So the output of that is a scalar. It turns out that they're equivalent, and you can show that if you require C positive and lambda positive, then having the element-wise product all equals 0 for every element in the vector, or having the dot product equal 0 end up coinciding in the case where both things are positive. But you can draw some pictures and convince yourself of this pretty easily. Basically, the idea is if you have a dot product equals 0, that means your things are orthogonal, right? And it turns out the only way for that to be true if both things are positive is for all the elements to be 0, which is kind of a fun little nugget. Maybe try to wrestle with that a little bit, but that's, I don't know, it's a true fact. So you can do it either way. There's a few different ways we'll see these written down. This is the one we're going to go with because it's the most kind of, this is the one that's going to show up in the code. So that's, I don't know, for your information. Okay, so, and we'll draw the picture one more time, and hopefully this will like make some of this stuff a little more clear for you. So same kind of picture we've been drawing, where we have, you know, say like x1, x2. So x is in 2D. So our f of x, our objective function, we're going to say right now is like a quadratic bowl. And I'm going to draw some level curves of the bowl. And then I'm going to draw the constraint here is going to be an inequality now. And it's going to be just kind of a linear inequality. We're going to draw it like this. So this would be the line here is c of x equals 0. And when we were doing this last time with the equalities, it had to lie exactly on the line. Now what we're saying is, like, let's say this side of the line is positive, and then this side of the line is negative. And so I guess strictly less than, strictly greater than, right? Because the line is the equality version. So what we're saying is, you know, the unconstrained minimizer here, say, is the origin. The bowl has a minimum at the origin, but we're saying you got to be sort of to the upper left of that line, right? So you got to live up here. This is the feasible region up here. So maybe I'll draw this as like a, I don't know, some light green. This is where you're allowed to be, right? Cool. Okay, so now let's think about these KKT conditions a little bit and draw some vectors and stuff. So we're saying, so in particular, right, which direction does grad C point in this picture? Up and to the left, right? In the direction of increasing C. So this is the normal vector to the constraint, right? And maybe draw some of these. Cool. Okay, so now, and then where's the gradient of F point? It's pointing outward, radially outward on all these level sets, right? Let's draw some of those. And in particular, right over here, they kind of look like this, right? So these are our grad C or grad Fs, right? Okay, so now let's think about that stationarity condition. So very similar to before, remember our whole thing is like the gradient has to be 0 in the free directions, same as last time. And that's kind of where that Lagrange multiplier thing comes in. The one difference here is now we have some sign business to worry about that we didn't have to worry about before. Namely, in the equality case, lambda could be positive or negative, it didn't matter. And that was kind of the idea that no matter what, the constraint has to like hold you on the line. Here, I only want the constraint to push me in one direction. I don't want it to pull onto the constraint, right? And that's kind of where the sign stuff comes in. So if we remember, right, like, and to be clear, right, notice like last time I had, you know, grad F plus, you know, whatever, dx transpose lambda and didn't matter. Here, the sign in there is important. So I have a negative sign on there. And let's just think about really quick for a sec, right? So you see the directions on grad C and grad F down there. They're parallel. They're pointing in the same direction, right? So now, if I say lambda's got to be positive, now for that thing to equal 0, right, I need to subtract lambda times grad C from grad F to have it 0 out in that stationarity condition, right? So the negative sign is key. There's a couple ways to think about it. One is this picture, right? I need to line those gradients up. And like forcing lambda to be positive means it can only push off the constraint. It can't pull me on the constraint, right? That's kind of the idea. And another way of thinking about this is that if you've got the Lagrangian and lambda's positive, you want constraint violation to make the cost higher. That's the other way, like heuristically, to think about what sign that should have. Okay, so here's a fun question. If I flip the sign on my constraint, if C of x has to be negative instead of positive, which is easy to do, right? What happens, and that's fine, you'll see that, right, in different books and papers. What happens to the sign on the lambda term in the stationarity condition if I flip C to be negative? Flips, yeah. Yeah, so that's right. So exactly, right. I need, like, if you just look at the directions of things, if I make C negative less than or equal to 0 and lambda is still positive, now that thing's pointed the other way, right? And now to zero things out, I'm gonna have to add instead of subtract. Is that clear to everybody? So the reason I'm belaboring this a little bit is you'll see this both ways. So you'll see conventions where C is negative, non-negative, non-positive. You'll see minus or plus in the Lagrangian or in the stationarity condition. You'll see all kinds of different things. Usually people always do lambda positive. That seems to be a convention, but you'll see the constraint either way. You'll see the sign in the stationarity or the Lagrangian either way. You'll see the complementarity thing at the bottom written a couple different ways, right? With a transpose or an element-wise product, all equivalent. And you just have to like either draw this little picture or think in your head, if you think about the Lagrangian, constraint violations need to be penalized in the Lagrangian. So constraint violations need to make the cost higher. So however you want to think about it, that's how you figure out what sign everything needs to be in here. Does that make sense to everybody? Cool. Okay. Questions about this?
Lambda is exactly 0.
Well, if lambda is exactly 0, that means you're in the feasible region and the constraint's inactive usually, right? So the idea, we talked about this again last time, but let's talk through this again, right? So what this whole complementarity thing is encoding is that either lambda or C has to be 0, right? One or the other always has to be 0. And what that's doing for you is if the unconstrained minimizer is in the feasible region and you're not up on the constraint boundary, it looks just like an unconstrained minimization problem. So you really just want grad F to be 0 and you want that constraint term to just drop out and do nothing, right? So in that situation, if C is greater than 0 and life is good and we're not up on the constraint, unconstrained problem, cool. We want that multiplier term out of there. So that in that situation, C is non-zero. For complementarity to be satisfied, lambda has to be 0. And that basically drops the constraint term out of the stationarity condition. And now it looks just like an unconstrained optimization problem, right? So if the constraints are inactive, lambda 0, constraint term drops out, all good. If the unconstrained minimizer is outside the feasible region, therefore the solution is going to lie on the boundary of the constraint set, right? It's going to lie on the C equals 0 line here. In that case, C 0. So now lambda can be non-zero by the stationarity condition. And that means that constraint term is going to show up in our Lagrangian, in our stationarity condition, and it looks like an equality constraint problem, right? So there's this concept of active versus inactive constraints. Inactive means you're in the interior of the feasible set, and the constraint doesn't show up at all, lambda 0, it just drops out. Active means the solution lies on the boundary of the constraint set, and then lambda turns on, and it basically looks like an equality constraint problem. So you can think of this complementarity thing as like a switching function that basically switches the constraint on or off, depending on if you're on the boundary or if you're in the interior. And if you kind of think about what that's doing, it's literally, if you look at stationarity, it's either making it an equality constraint problem or an unconstrained problem, right? So all this extra KKT baggage is really just encoding the on-off switching of active and inactive constraints. Does that make sense to everybody? Yeah.
You could have like you just have this linear.
Yeah, this is a little subtle. I mean, the right answer is that it's like really not really doing either of those things, and it's solving like a root finding problem. When I say that here, it kind of holds up in this case, modulo some caveats, but it's a heuristic for that I think is helpful for understanding like how to figure out what that sign is. The right answer is to look at this picture and see which way those normal vectors are pointing and say, okay, for stationary to work out, if lambda is positive, I have to subtract now. If lambda is positive and they look like this, i.e. the sign's flipped on the constraint, I need to add to cancel those out, right? So that's the, I would say, the better way to think about it. You can also think about it as if lambda is positive and I look at the Lagrangian, it's got to be a penalty. But yeah, you're right. In the equality case, it doesn't really hold up. Okay. Any other questions? Okay, so this is good. Everyone likes KKT conditions. Excellent. Okay, so now we get to like sort of, tell you how life is hard again and how things are not as easy as we would like them, but we'll get through it together, okay? So so this seems fine. And remember last time we basically wrote down these necessary conditions in the equality case, and we just straight up threw a root finding algorithm at these first order necessary conditions, right? We just did Newton on these things in the equality case. Unfortunately, in this inequality case, we can't just throw Newton's method at this, sort of for obvious reasons, right? This is not really a root finding problem. It has inequalities in it, which is kind of weird. And it turns out also that last condition, that complementarity condition, is actually horrible and non-smooth. Like it's literally a switching function, right? So it sort of should be unsurprising that its derivatives are not well behaved, and it sort of is a non-smooth thing. And therefore you can't just throw Newton's method at this and have it work. So you have to play lots of games and do some tricks. So we're going to tell you now about some of the tricks you can play, some of the strategies, and then dig into one particular strategy that that works. But there are others, right? So let's write that down. Oh, weird. Got a very fat pen somehow. Okay, so unlike the equality case, we can't directly solve these things. Okay, so what do we do? So there's lots of ways, unsurprisingly. I will tell you about a few. So now we'll kind of briefly survey some of the options, the common options out there. So the first one, and maybe the conceptually simplest one, is called the active set method. And the general strategy is you guess which constraints are going to be active and which are going to be inactive somehow, or you have some oracle that tells you this, right? You have some strategy for knowing what the inactive and active constraints are. And then if they're inactive, you just throw them out. And if they're active, you turn them into equalities. And then you just solve an equality constraint problem. And we're back to what we know how to do, right? And the reason this is a thing is, right, going back to that switching stuff is non-smooth, non-differentiable. I can't just throw Newton at it. So what we do is use some outer loop heuristics to decide which are going to be inactive and which are going to be active, and then turn it into either throw them out or enforce them as equalities, solve an equality constraint problem. Cool. So let's see. Switch equality. I guess inequality constraints on or off, and solve an inequality equality constraint problem, which we know how to do. Okay, so thoughts on this? Why is this a good or bad idea in general? I don't have any feelings on this. Yeah. Yeah, that's good. Yeah, so basically, if you have a good heuristic for knowing what this active set should be, this can work extremely well. But if you don't have a good heuristic for guessing the active set, in general, this scales combinatorially in the number of constraints. Basically, if you don't have a good heuristic, the worst case complexity of this is awful. Basically, in the worst case, you have to check every possible combination of active and inactive constraints, which blows up in the number of constraints in a really terrible way, right? So if you have a good heuristic and you're warm starting and you can guess right, this can work really, really well. Turns out there's many control applications where that is the case. Actually, in model predictive control problems where you're warm starting all the time and you're only ever like doing small updates on the solution, this can be extremely effective. And this was kind of behind the success of like the MIT DRC team on Atlas. They developed a custom QP solver where they were really good at guessing what the active constraints are. They guessed right the first try like 90% of the time, and on the second or third try in all other cases. And because they had those really well dialed heuristics, they were able to solve the underlying sort of MPC problems way faster, and they got like giant speed ups, and that's how they ran their control loop in real time. That's in the papers on like that stuff from like 10 years ago. So can work really well. But in general, it's not a general purpose strategy, right? It requires like custom problem specific tailored heuristics for guessing that active set well. But this is a game worth playing on some control settings where you can do this effectively. Okay. Any other questions on that? Make sense?
What the constraint problem we can solve has. Could there be a gap between what I'm solving and what the inequality constraint actually?
If you guess the active set right, if you get it right, that equality problem is the exact solution. Like that's it. And it's easy to tell if you guessed right or not. Basically, if you guess wrong, you check the constraints after the solution, right? So you'll see constraint violation if you guessed wrong. Like basically, if there was a constraint that should have been in the active set that wasn't, the constraint will be violated. So that's easy. What happens if there was a constraint that you put in the active set that shouldn't have been there? How do you know that? Nope. 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 Think about the KKT stuff and think about the difference between this case and the equality case. Nope. Yeah, hold on.
You not end up on the line.
You'll end up on the line for sure. So if you're on the line because you enforce it as an equality, but you shouldn't have been on the line, you should have been in the feasible region, what does that correspond to in terms of lambda? Lambda will be negative. It'll have the wrong sign. So if you put it in the active set and it shouldn't have been there, that means the solution's naturally in the feasible region. Lambda should be 0. It means you're pulling it onto the constraint rather than pushing it off. So that means lambda is going to have a negative sign on it because it's pulling right towards the constraint, which is not what you want. So that's how you tell, right? Basically, if it's in there and it shouldn't have been, lambda will come out negative in the solution. So you drop it. If it should have been in there and it's not, then C will be negative, right? Makes sense? So this is easy. So you just try a bunch of combinations until you guess right. Cool. Okay. So that's active set. Can work well if you have good heuristics. Generally, though, not a good. So it's not a good idea for general purpose stuff because you just, in the worst case, is really bad, right? So if you can't guess what. Okay. So the next option, and these go way, way back, you know, and are super sort of dumb and intuitive, are so-called penalty methods. And probably everyone has tried naive stuff like this. And in general, it's not a great idea. Doing this naively is bad, basically, and I'll tell you why. So the idea here is you replace the constraints with cost terms that penalize constraint violation. Okay, so for example, you might take our, you know, prototypical thing here. And like, I don't know, let's say we have like, you know, this guy, C positive. We're going to take this and we're going to introduce a penalty term into the cost that, you know, penalizes violations. The most standard kind of first thing you might think about is a quadratic penalty. And so in this case, where it's an inequality, that would be implemented like so. So we'll like clip the, you know, the C of X, right? So we're only penalizing negative C, right? We don't want to penalize positive C because that's good. And then we'll just take that and square it, right? So like the picture of this would be something like this is X and this is like C of X. It's 0 in the interior here. like we're in the feasible set, and then it's some quadratic function as soon as you start violating, right? Okay, why is this a bad idea? So I guess if we were going to do pros and cons, this is obviously really easy to implement. Okay, why is it a bad idea? Yeah. It won't in general, right? Like it'll always violate a little bit. And that's kind of getting at the answer here. So what would you do if you went and solved this penalized problem? You're definitely going to get something that violates a little bit, right? Because the penalty doesn't turn on until you're violating. So it's always going to violate a little bit. What if you get, but you know, fine, there's some tolerance that you care about hitting, and like, you know, after that you don't care. So let's say you solve it and it's violating a little too much for your taste. What do you do? That's right. So you'd crank up that row, right? Okay, so what happens then?
Super negative straight. It's like violent. So if we got them together, you're still gonna get something that's like a better solution.
So yeah, you're kind of headed in the right direction. So how high do I have to crank row up in general? That's right. So basically in this setting, to get perfect constraint satisfaction, to like really land on it, you have to drive that row to infinity. And basically that's numerically terrible. You can't do it. So you can get into situations here where to get to some reasonable constraint tolerance, you have to jack that row up really high. And then your conditioning just goes to crap and the numerics are bad and floating point round off, blah, 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 and you can't solve the problem. So the like legit term for this is ill conditioning, right? This method gets horrendously ill conditioned as you jack up the row to try to get the constraints to be satisfied better. The other issue, if you're paying close attention here and nitpicking this, is what does the derivative of that penalty function look like at the origin there, or whatever, at c equals 0? Well, okay, so is this function continuous? The function's continuous. Is its first derivative continuous? It is, yeah. It's flat, and then the quadratic is flat there too, right? So it's C1. What about the Hessian? The Hessian to the right is 0, and the Hessian to the left is rho, basically, right? Times, so it's something like that, right? So the Hessian is discontinuous. So if you're doing gradient descent, like a first order method, totally fine because it's C1. But strictly speaking, if you apply Newton's method to this, it's a little sketchy. It turns out it still works fine in practice, so it's not such a big deal. That ill conditioning problem is a much, much bigger deal. You can just throw Newton at this and it kind of works, but the like legit theory of convergence on a function like this that isn't C2 smooth for Newton's method is a little sketchy. It turns out it still works, but there's lots of gotchas in it. It turns out that the convergence rate drops off. So you don't get quadratic convergence on stuff like this, at least not at that point, which is in practice not a very big deal. So maybe someone was going to say that, which I'll just give it to you. Like it turns out you might think that's a problem. It turns out it's not really a very big deal, practically speaking. This ill conditioning thing, though, is a big deal. Okay, so let's write that down. Kind of, sort of, not really. It turns out like if your Hessian's only discontinuous at isolated points, which is the case here, it turns out it doesn't really matter and it still works. Like said another way, right? Like the discontinuity in the Hessian is like on a set of measure 0, right? It only happens at this like infinitesimal point. And so as a result, like it still kind of works out. There is legit theory on this that like you can prove it still converges. But the legit theory says that it still converges, but the convergence rate is worse. It's not quadratic anymore. In practice, this doesn't really matter a whole lot, and it's still fine. Okay, so that. Basically, this has issues with ill conditioning. And this all kind of stems from the fact that you have to crank rho to infinity to like legit satisfy the constraints. And as a result of this, like the end result is you're going to hit some ill conditioning somewhere as a function of that row cranking up. And the net result of this is you can't really solve these problems to high accuracy with this method because of the ill conditioning problem. Okay, so these have been around since the dawn of time, right? That's like sort of obvious and the first thing you're going to try. So yeah, I mean, it means you're going to have this thing like have to blow up to infinity to get this to converge. So you can't do that in floating point math. Strictly speaking, what ill conditioning refers to in this problem is that the Hessian, if I do Newton on this, like where this shows up practically and where you would care is that the Hessian matrix of this thing, when you compute it, is going to have a huge spread in its eigenvalues. Do you know what the condition number of a matrix is? So it's the ratio of the largest to smallest singular value of the matrix, right? And the sort of heuristic in numerical analysis is that if you solve a linear system, so if I solve ax equals b, basically like factorize a or compute a inverse or something like this, you're going to lose sort of base 10 log of the condition number of a, number of digits of accuracy in your answer. So if your condition number is like 10 to the fifth, you're going to lose 5 digits in your answer. So how many digits is a double precision floating point number? About 15 or 16, right? So if it's 10 to the fifth, no big deal. You'll lose the last 5 digits. Well, the last 5 digits will basically be noise, but you'll get 10 good digits in your answer. What if, condition number is 10 to the 10th, 10 to the 12th? You're hosed, right? So the answer's garbage. So that's what we're talking about. And that's why it's an issue. Does that make sense? So that's like the real kind of thing. But this issue is like it's a bigger issue. It's a broader issue. This kind of ill conditioning issues. Basically, it's kind of like saying the function has like very high dynamic range in some sense. And it also like this specifically in Newton's method, it manifests itself in that Hessian's going to be really jacked and solving a linear system is bad. But it also affects first order methods. So if you took the same kind of ill conditioned problem and tried to do gradient descent or SGD on it, it would also behave terribly and not really work for very closely related reasons. Does that make sense, everybody? Okay, cool. Where were we? Okay, any questions about this? Okay, so the last note on this is right. So this has this issue. Everyone's known about this. People have been doing this since computers were invented. So there's been like lots of kind of hacks on top of this to try to fix the ill conditioning issue. Some more legit than others. The more legit way of fixing this issue, one of the more legit ways is called the augmented Lagrangian method. And my lab spent a lot of time working on these methods. And if you go back to previous years in this class, we spent a lot of time talking about AL. The gist is you introduce a Lagrange multiplier in addition to the penalty term, and you use the penalty value to estimate the Lagrange multiplier. So you kind of offload the penalty at each iteration into a multiplier estimate. And the reason that's good is it turns out if you do that, you're also going to converge on the Lagrange multiplier, and you don't have to crank rho to infinity anymore to get the exact solution. So that's kind of one method for dealing with this that works in practice and is decent. And it turns out that's been around for a while too. People have been doing that since the 60s or 70s. Very effective, was very popular for a while. It kind of decreased in popularity in the 80s and 90s, but it's now back again and is hot again in the last few years under the name of ADMM, alternating direction method of multipliers. Who's heard of that? Yeah, so that's what ADMM is, essentially a small twist on the augmented Lagrangian method. So these are closely related. The gist is you do a penalty, but then you do some kind of outer loop Lagrange multiplier estimation based on the penalty. And that sort of saves you from this infinite blow up of the penalty issue. And there's many variations on this, augmented Lagrangian, ADMM being kind of the main kind of kind of ideas. Okay. Yep. Yeah, it means you're not solving a primal dual problem for both x and lambda. You're only minimizing that penalty thing over x. But then given the solution to that, x minimization, you look at the value of the penalty term, and you basically take that and stuff it into a lambda estimate. So you kind of like are estimating lambda in this outer loop way. And like one heuristic kind of way to think about it is you're offloading the like forcing that the penalty is doing into a lambda estimate term. And by doing that kind of at each iteration, you're converging on a estimate of the primal dual solution in a way that's like preventing you from having to like jack that row all the way up. That's kind of the gist. And I mean, these are actually pretty straightforward to implement too. But the message is like you need some extra hacks and tricks to make a penalty really work. So if you're ever tempted to do a penalty thing, go look up augmented Lagrangian, or go and check some of the stuff from this previous editions of this course, and you'll see how to do that in ways that kind of work better. There are ways to make it work. Okay. Any questions about this?
We established equality constraints of optimization. We have the function f of x, and let's say we have rho f of x. Rho f of rho, just like the magnitude of function
Yes. If you put like basically the issue is you have really, really big and really, really small numbers in the same problem. That's kind of the core issue. And this can manifest, right, that you have like huge dynamic range in like the derivatives or the Hessians, right? And that's going to show up in your kind of Newton solve. And because of like the finite precision of double precision arithmetic, you kind of can't handle that. And as a result, like at some point, you're just going to lose accuracy in the solution, or you just can't solve the problem. Okay, cool. So that's that. Don't do penalties. Sort of same advice as Ford Euler. It's bad for your health. Don't do this. There are better things to do. Go look it up. So now we're going to talk about is kind of the other method of choice here, which I would say is kind of, at least for convex problems, like kind of the industry standard thing. And that's what we're going to kind of dig into and show you how to really do. And these are so-called interior point methods, or sometimes referred to as barrier methods. Who's heard of this before? Okay, decent number of people. Okay, so the gist here, it's on its face. When I first show it to you, it's going to feel a lot like a penalty method, but it's different in some key ways. So the idea here is we're going to replace inequalities with a so-called barrier function in the objective. And again, it sounds like a lot like a penalty, but so yeah, we'll do the simplest possible version of this for now. So I'm just going to write, x greater than or equal to 0, right? But in general, same stuff. So if I have this, the standard barrier function to use is a so-called log barrier. So I'll write it down, we'll draw a picture. So we're going to change it over to this. And rho is a similar kind of, like barrier parameter that we can scale as we solve the problem to converge. So that's it. And so what this looks like, if we remember what a log looks like, is something like this. So I have, kind of x here, and then say minus log of x up here. So this looks like the following. So it's almost 0 in the interior. And then as you get close to the boundary, it blows up to infinity. But importantly, right, it's continuously differentiable, all that good stuff, right? It has all the nice derivatives that you want. Okay, so why is this? This seems like maybe a bad idea, right? Like it clearly gets like super steep here, and it blows up to infinity at the constraint boundary. Blowing up to infinity seems like a very bad thing from a numerical perspective, right? Like, so what's different about this versus the penalty, and why is this like maybe a good idea? You don't have any thoughts? first of all, there's like what's different about it qualitatively versus the penalty method. Yeah,
It's non-zero before negative.
that's exactly right. And that goes to the fact that it's got continuous derivatives, right? Log's an analytic function. You can always compute gradients and Hessians, and that part's good. Why is it called an interior point method?
Because it stops you before you pass your.
That's right. Yeah. So this is like the most important qualitative difference between this and a penalty. So penalties don't kick in till you're already violating the constraint, right? A barrier, on the other hand, is designed such that you can never violate the constraint. So it blows up to infinity, makes your cost is infinite on the constraint. So you can never get there. It's keeping you strictly in the interior. So a side effect of this is to initialize an interior point method, like naively, the way I've written it down here, you have to start with a feasible guess. Your initial guess has to be feasible with respect to the constraints. Otherwise, this penalty term is going to be infinity and you're hosed, right? And that can be tricky, but there's a trick for getting around this that we'll talk about. It's so-called infeasible start trick. Okay, so those are kind of the big deal differences. Naively, you would expect this to have numerical issues as well because of this infinity thing. And historically, these ideas were come up with around the same, 50s, 60s back in the day. And they were abandoned back then because indeed, if I write it like this and just try to minimize with respect to X, it does have ill conditioning problems, just like a penalty method, like you would expect. But there's a trick that was that people figured out in the 80s to get rid of the ill conditioning. And that makes these work beautifully. And there's like a really rich theory behind these, and these are awesome, basically, with the trick, the so-called primal-dual trick that we'll talk about now. Okay, cool. So let's see. Things to say about this before we dig deeper is these are basically the gold standard for convex problems. So like to first order, if you have a convex problem that's like of moderate size, like not insanely huge, this is the thing to do. Like this is the first thing you should try. Like it's kind of the standard, right? This thing, you can throw Newton's method at it. And because that thing's continuous, the derivatives are nice everywhere, you can get fast convergence. And this stuff, we'll get a little into it, has really strong theoretical properties. Basically, you can give all kinds of guarantees about these methods. If you throw Newton's method at it, it converges quadratically, and you can actually bound the number of iterations it'll take. So you can give hard real-time guarantees. You can say for sure, if you give me a feasible problem, this is gonna solve it to some precision in some finite number of Newton iterations. And therefore you can actually say exactly how you can give a time budget to this, right? And this is really key for doing online control. I can tell you exactly how many Newton steps it's going to take and that it will converge and guarantee everything. And then you can trust this in a real-time setting, right? And just for your reference, right, we're gonna there's lots of solvers that implement this stuff, and one that we're gonna use in here a bunch later in the course is IP-opt, which is actually out of CMU, Larry Beekler's lab, and it's one of the most popular like large-scale nonlinear programming solvers. So you will use a sort of industrial strength one of these later, and doing an industrial strength version is hard. There's lots of extra tricks that you need. But we're gonna kind of like do the baby version in here, and you're gonna implement your own. Okay, so this is kind of like the intro pitch. Any questions about this before we like get into it? Yeah.
Qualitatively, how does the
In general, it's like super problem dependent. There's like pros and cons about all of these things. And if you care about like being as fast as possible on a particular problem, you can kind of play lots of tricks and use lots of heuristics, and because you know certain things about that specific problem to go faster. So that idea, it goes by the name the no free lunch theorem in optimization. It's basically saying if you can special case to a particular problem, you can always do better. But if you try to be general purpose, there's no free lunch, right? Like if you make your solver dialed in for one particular problem, it's going to almost necessarily be worse at some other problem, right? So in general, there's no free lunch. That's kind of the idea. So it's all a game of trade-offs. So like if you have a specific, like a control problem on a particular robot and you know some things about the setting, for example, like we already said, right? If you have a good heuristic for guessing the active set, then maybe an active set method is going to be the fastest, right? If I can guess right 95% of the time on that active set and then guess right on the second try, the other 5% of the time, that's going to be faster than anything, right? So that, I mean, it totally depends on the setting, right? So there's no general takeaways. The nice thing about these interior point methods, though, is in the general case, they have good sort of worst case general purpose performance. So if you don't know anything about your problem, like if you're prototyping and whatever, and you just need it to work, these are going to work well, basically like on a convex problem. There's some, the worst case is good. Whereas in these other methods, the worst case can be really bad, right? And you have to like do a lot of hand wringing and tweaking and hacking to get it to perform really well. I don't know if that helped. Okay, cool. Anybody else?
It's also nice because the problem stays convex, you can have change volumes.
Yes. Yeah. So that's also a true fact. Yeah. So these are like excellent for convex problems. Like if you have a convex problem and it's not too big, do this. For non-convex problems, the story is a lot murkier and much harder.
These methods work often example of people reach it but damage.
They will reach it asymptotically as a function of rho, and you can get as close as you want to. So like if you give me some tolerance on the solution, like 1e minus 8, I can hand you a solution that's good to that tolerance. That's will actually decrease here in a way that's a little funny to understand. So basically, as I decrease rho here, that pulls the corner in closer and closer, right? It still blows up to infinity, right? Yeah, makes sense. Okay, cool. Okay, shall we get into it? Okay, let's do this. So now what we're gonna do is actually like walk you through how to build one of these things in some level of detail. So the first order business is to talk about the so-called primal-dual trick. And so this is the magic trick for getting rid of the ill conditioning. This was invented in the mid 80s, and it was like this huge deal in optimization theory. And the reason is that these methods, this primal-dual interior point method thing, it's a practical thing that gets you provable polynomial time solutions to convex problems. Before that, there were not really polynomial time algorithms for solving convex problems. Like in general, it was kind of this active set flavored situation where you'd have to guess all the combinations, and the worst case complexity of that is bad. These have provable polynomial time complexity. So that was kind of huge deal. Okay, so we're going to look at the simpler case again. Okay, so as simple as we can do. So this guy. So just x positive, right? And think about just the scalar case. So we've turned this into an unconstrained problem now. And now I'm going to ask, what are the first order necessary conditions? We're literally just going to set the gradient equal to 0 for that thing, right? So partial f, partial x, minus, and so derivative of log is 1 over x, right? So this thing is just rho over x. Okay, so this is the thing I would solve with Newton's method, right? This is the gradient equals 0, stationarity, whatever. I've gotten rid of the constraint, it's just this. So sort of obviously, back to the ill conditioning conversation, the solution to this guy, might lie on the boundary, i.e. at x equals 0. What happens to this thing as x goes to 0? It's 1 over x. It's going to go to infinity, and that's horrible, and all the ill conditioning badness will happen. So how do we get rid of that? So let's write that down, I guess. So this I would call a primal only, right? There's no multipliers here. There's no dual variables. This is a primal sort of formulation of the first order necessary conditions. This guy blows up. As x approaches the boundary. This is bad. We don't want this. So there's a trick to fix this, which is pretty fun. And once you've seen it, it's sort of obvious. But it has some deep insight. So we can fix this with the so-called, I don't know, I call this the primal-dual trick. Someone might have a better, more legit name for this. I don't know. So what we're going to do, as the name implies, is we're going to introduce a new like dummy variable that I will suggestively call lambda. And it turns out it's going to become like a Lagrange multiplier. But it's not obvious at first that it is that. So we're going to introduce this new variable lambda, and I'm going to set it equal to that second term in my first order necessary condition. So I'm going to set it equal to rho over x. And I'm going to, if I stare at that for a second, and again, assuming things are scalars here for simplicity, I can rewrite that as x times lambda equals rho, right? I just moved the x over to the other side. Everyone cool with that? This is also subjective. This should look like something we just saw. Someone know what that is? Okay, so I'll now write this down. So we now have, instead of just x, we have two variables, and I made this just trivial substitution. Nope. Yeah, what happened? What's different about this versus the complementarity we already saw? Equals rho instead of equals 0 now, right? Okay, so that's actually kind of a big deal. Okay, so let's rewrite this now. So I went from, so that top line now, right, this df dx minus rho over x is now df dx minus lambda, right? And then I have this second line now that it's x times lambda equals rho. Trivial, all I did was introduce a dummy variable and set it equal, and now I have this new thing in two variables, right? But if you stare at this for a second, it should be pretty clear that this lambda is actually taking the same place as a Lagrange multiplier would. And this second line is a relaxation or smoothing of the complementarity from the KKT conditions, right? So instead of x times lambda equals 0, it's x times lambda equals rho. The way to think about this is, right, x times lambda equals 0 is this hard switching thing that's not differentiable, blah, blah, blah. Another way to think about that is it's a brick wall penalty, right? It's 0, and then it blows up to infinity at precisely at x equals 0. And what we've done is taken the brick wall and smooth it out with that rho on the right-hand side in such a way that now it's differentiable. So there's like sort of deep connections between the log barrier thing and the KKT conditions. That's kind of the message here. And you could think about the log barrier thing as some kind of smoothing of the KKT conditions in a fun way with this trick. So this guy is a relaxed complementarity on those KKT conditions. Okay, so so now it should be obvious with this kind of trick. What do I have to do here to get this to converge to an exact solution of the KKT conditions? Drive rho to 0, right back to our initial thing. So if rho equals 0, this is exactly going to satisfy the complementarity condition and then exactly satisfy KKT. But in the limit as rho goes to 0, remember before over here, in the limit as rho goes to 0, like this thing blows up right at the boundary. Now I've completely gotten rid of that 1 over x behavior, right? So now this is like numerically benign. There's no 1 over x anymore. There's no, but the trick is as you drive rho to 0, this like starts to approach that hard switching stuff and becomes non-differentiable. So basically you can drive it arbitrarily close to 0 in practice, but you can't set it to exactly 0. So you drive it as far as you care from a tolerancing perspective. Okay, so this converges to exact KKT solution as rho goes to 0. And essentially what you do is lower this kind of gradually. As the solver converges. from say like, I don't know, like rho equals 1 to maybe rho is like 10 to the minus 8 or something like that. It just depends on how far you want to go, right? From a tolerancing perspective, but you can go pretty much as far as you want. Let's see. No, so like this is cool, but we're missing the other two lines from the KKT conditions, right? Notably primal and dual feasibility, those inequality conditions. So it turns out if I start in the interior, if I start this thing off in the interior, it'll stay there because of the log barrier properties. So we kind of don't need the other two conditions explicitly in our Newton solver as long as we start feasible, but you still have to make sure they're satisfied because of when we take a Newton step, we're approximating everything, we're linearizing everything. So what can happen here if you naively do this is the Newton step can step across the barrier because of its linearization kind of approximations, and then you're hosed. So to get these things to work in practice, you don't have to explicitly have those other two terms in here, but you have to have a line search that backtracks and checks the constraint and make sure you're always staying in the interior and you don't step across the barrier. And that's actually kind of subtle and tricky to get right. Okay, so note, we still need to enforce sort of x positive and lambda positive. You do this in the line search. Yeah. But this is tricky, so we're going to kind of show you another way around that. Yeah, so we're going to take another approach. And specifically, I've always shied away from teaching this stuff in here because the line search details are really gnarly and you need a lot of tricks to make this work. And it's sort of too much work to teach. But we're going to do something fun here that's actually super new. So I'm going to now show you something that I think cleans this up super nicely. I'll just tease the paper real quick. So this is a paper from 2 years ago. This is all like kind of very, very recent state-of-the-art stuff called log domain interior point methods. Here's the paper. It's on archive. You basically won't find this anywhere else. This is a guy, Frank Permenter, who's at TRI and came up with this trick. It really makes this a way easier to understand and implement. So I'm going to teach it to you. If you want to go read the paper, I recommend that's the paper. I'll post it somewhere, post it on Piazza or whatever. It's a little gnarly, so I'll show you like the simplest way into it. But yeah, I don't know. It's kind of cool. It's a 2-year-old idea that isn't in any books or anything yet. But it's super nice. Okay, so let's do it. Yep.
So the reason line search oversteps is because we keep templating down nice one value.
No, it's really just like you're linearizing everything. So with that linear approximation, you take a Newton step, the linearization can take you across the barrier because you're linearizing, right? That's it. So then your constraint's now blown up. So in order to like keep everything on the rails, you have to backtrack until you're back inside the feasible region. So that's how historic, like standard primal-dual interior point methods do it. And there's lots of tricks for doing that well and having it like still converge fast and all that. Yeah. Turns out so you have to use a backtracking line search. Yeah. So the trust region idea is sort of often implemented with a log barrier. It's sort of tricky, but yeah. So if you're familiar with like sequential convex programming and those ideas, they're literally enforcing the trust region with a log barrier. A lot of those. So yeah, this is sort of one level deeper in the stack, if you like. And here, yeah, you got to use a fancy line search or do what we're going to do now. Yeah. No, this is literally just the constraint function C of X is the identity. It's a trivial C of X. Makes sense? In this case, C of X equals X, right? I just try to make life easy for drawing pictures and stuff. We're going to do the general one now. So we'll go back to, okay, so this is called the log domain interior point method. It's a nice trick. We'll call it the log domain trick. Okay, so now we're going to look at the more general case. So we're going to have min of f of x subject to C of X greater than or equal to 0. So now we're going to simplify this or make our lives slightly easier. By introducing what we call a slack variable. That's a generic word in optimization for introducing new variables that don't change the problem. And the gist here is I don't want to have that C of x inside the log barrier because it's annoying and it makes everything harder. So I'm going to just introduce this new slack variable that we're going to call s. So we're now going to optimize over x and s. And we're just going to do the following thing. So we're going to have an equality constraint. We're going to set C of x minus s equal to 0. And then we're going to set s to be non-negative. So s is going to go inside the log barrier. So we have like just the s in the log barrier makes the math nicer. And then we're going to enforce c being positive via that equality constraint. Does everyone see how that works? So for this two sets, this equality and inequality together to both hold, c of x has to be positive. So it gets you the same net result. It's mathematically exactly equivalent. This just makes the math nicer to have this slack variable. So this is a kind of a general trick, sort of idea. This is slack variable thing shows up a lot. So now I'm going to do the log barrier thing on this. So we're going to end up with min of x and s, f of x minus rho log of s. And then we still keep the equality constraint around, right? Okay, so far so good. Now we're gonna sort of do the stuff we know how to do. Now we just have a very vanilla equality constraint problem like last time, right? So we're gonna write the Lagrangian down and turn the crank on that. So we're gonna have L of x, s, and lambda. And we've got this stuff stays the same. So this is the objective now, right, in terms of both x and s. And then we have a Lagrange multiplier term for the equality constraint. So this one just looks like this. All right. So far, so good. So now I'm going to set all the gradients equal to 0, write down first order necessary conditions of this guy. And remember, this is an equality constraint problem now, just like we did last time. So we've got grad x of the Lagrangian is going to be grad f minus partial c partial x transpose lambda equals 0. So this is like stuff we've seen, right? No problem. Now I'm going to do gradient with respect to s. This is going to be minus rho over s plus lambda equals 0. Everyone cool with that? And then the last one is gradient with respect to lambda, which is just spitting the constraint back at us. So s minus c of x equals 0. Okay, so this middle line, what does that look like? What's the move there? You can tell me. That middle line is exactly this like relaxed complementarity thing that we've already seen, right? So we're going to rewrite it that way. So this is s times lambda equals rho. This is our relaxed complementarity again. Okay, so this is all good. We've seen this already. But remember, the key thing we're missing here is we still have to enforce s and lambda have to stay positive, right? So here's this log domain trick that makes us basically not have to worry about that anymore. And it's obvious, in hindsight. So we want to ensure s is positive and lambda is positive. Remember, historically, we'd use some fancy, crazy backtracking line search stuff for that. It turns out, trust me, it's super annoying. We're going to instead, play this trick, we're going to introduce a change of variables that takes advantage of that complementary slackness thing. So we have s times lambda equals rho. So I'm going to make s equal to square root rho e to the sigma. So we're instead going to have this sigma variable. So if that's true, and I look at s times lambda equals rho, what does lambda have to equal? sort of suggestive here. You know what I'm tell me for that equality thing to hold up? It's got to be square root rho e to the minus sigma, right? E to the sigma times e to the minus sigma is 1, and then square root rho squared is rho. So because of that relaxed complementarity, if I make S this, it sort of means lambda has to be this. And why is this a good thing? So now complementary slackness, that complementarity thing, which is the annoying thing, right? That's the annoying thing when we had to relax and all this. Now it's redundant and it goes away. I don't need it anymore in terms of this new variable. It's in terms of sigma and this change of variables, it's satisfied by construction always. And the other cool thing is now, can S or lambda be negative? No, right? Because they're in that exponential. So S and lambda are also now guaranteed to always be positive by construction. So I've gotten like kill two birds with one stone, whatever you want to say it. I've enforced positivity of S and lambda now always by construction, and I'm always satisfying the relaxed complementarity always by construction. So now those totally drop out of the problem, and I have a much, much nicer, simpler problem that's much easier to solve. So now this relaxed complementarity is always satisfied. And so now we're just going to plug this back into those KKT conditions and simplify everything down a little bit. Or yeah, I guess properly speaking, first order necessary conditions, not strictly KKT. We'll try to be pedantic about this, I guess. And remember, now we got rid of one of those, right? We got rid of the relaxed complementarity entirely. So dx transpose, and now we're going to plug in the substitution for lambda. So it's square root rho e to the minus sigma equals 0. And then we've got the constraint one. So this is c of x. Now instead of s, we've got square root rho e to the sigma equals 0. That's it. So now this looks basically exactly like a very vanilla equality constrained problem. And we just throw Newton's method on this. Yep. I made it up. It's a change of variables. So that S equals square root rho e to the sigma, I just made that up as a change of variables. The reason I chose that is because it guarantees S stays positive, right? And then the side effect is if I plug it into this relaxed complementarity up here, S times lambda equals rho. If S is that, then lambda has to be that in order to satisfy that condition. So now with this change of variables, I got rid of the complementarity line. It's always guaranteed to be satisfied. And this also takes care of the positivity constraints automatically. So I've now gotten rid of all the messy, annoying parts of this KKT conditions, and I got it down to just these two lines, which are now smooth, nice functions of x and sigma. And I just throw Newton's method at this, and it works. Yeah. In principle, yeah. Like in principle, you can do whatever you want. This is a particularly nice choice because it satisfies these properties, right? But in principle, you could come up with something else that also had these same properties. Yeah. So this is a trick that someone came up with 2 years ago. That's oh yeah, the square root is there for convenience, right? You could like put all the row on one of them and not on the other, whatever. But this is kind of symmetric in a nice way and works out nicely, it turns out. Okay, so we're gonna go do this. Yeah, any other questions about this? It's a super, super clean, nice trick that, makes this all nice. So, all right, just to kind of, we can solve this with Newton. Or, Gauss-Newton if you want, like we talked about. And this is going to look like, again, a KKT system. So we got some Hessian, bringing it up with square root rho C transpose e to the minus sigma over here, C minus square root rho e to the sigma times delta x delta sigma equals minus grad f plus c transpose through rho sigma. This is just me like writing out the kind of Taylor expansion, the Newton stuff, right? That's what it looks like if you turn the crank. Pretty nice. Okay, so we're going to do this, and we're going to do it on a specific example. Apparently, this is not a good enough F. So we're going to do this on a particular problem class called a quadratic program. Who's heard of this before? Decent number of people. So this is like bread and butter applied control. Like this is like super common in control, and we're going to do lots of this. So you're going on the homework, first homework, you guys are going to write a QP solver this way, and I'm going to give you like a little bootstrapping. So a quadratic program is a quadratic objective, and in order for this to be convex, Q has to be positive definite. And then we can have, in general, linear, so AX greater than or equal to B, inequality and equality constraints. So that's, these show up all over the place. So super useful in control. We're going to see lots of this. And the real reason these are super useful is because we know how to solve them really fast. There's solvers out there that can solve these kind of QPs at kilohertz rates. So you can do real-time stuff. If it's a convex QP like this, you can guarantee the solution time. You can guarantee that you'll find the solution, blah, blah, blah. So that's why we like them. Okay. And this is like under the hood on like all the cool, MPC controllers on quadrupeds and humanoids that you're used to seeing. Yeah. I mean, you're going to do a backtracking line search inside this guy. Yeah, so that in other words, that doesn't ever go away. Yeah, we're kind of bootstrapping and bootstrapping and bootstrapping here, right? So like basically, I showed you how to do root finding. Then we did minimization by turning minimization into root finding. Then we did equality constrained minimization by turning it into like root finding. Now we're turning inequality constrained minimization into equality constrained minimization, which we already knew how to do with root finding. But all of these, in general, like you're all still having to do line searching and regularization and all the rest, right? So we're going to get into that some more. But let me pull up the code, and we'll go do this. And hopefully this is, oh, what the hell? This is going to be hopefully useful to you on your homework. Okay, so here's the code. It's like stuff we've done a bunch of. So we're going to do a QP. It's exactly the same, kind of setup we've been looking at a whole bunch. So let's take a look. Okay, so yeah, it's this quadratic bowl, and then inequality constraint where we need to be up here to the left, right? So the picture I've been drawing all along. And now I'm going to write down a few things. So this is the exactly what we just wrote down. This is the residual function. These are the first order necessary conditions that I need to be 0, right, for this log domain interior point thing to work out. What we just wrote down is the 2 lines, right? Cool. And then I'm also, just for our own educational purposes, going to write down the true exact KKT conditions as well. And we're going to check these to make sure we hit them, right? So this is, again, stock KKT conditions that we've already seen, right? Okay, so now we're going to do this and try some stuff. So I'm going to start us off over here. So we're in the interior, right? That's good. And this is the true minimizer, and sort of intuitively, the solution here in the constraint case is going to be like right around there somewhere, right? It's going to be on the boundary as close as we can get to kind of the true minimizer. So I'm going to start this thing out at rho equals 1. So it's going to be nice and smoothed out, right? And we'll check the interior point. So this thing has a residual, and then the KKT residual as well, just for fun. We need all this stuff to be 0 pretty much, right? So now, oh, this is stupid stuff from debugging. Here's the main meat. So this is a Newton solve. Inside here, we're going to evaluate that residual, and then we're going to have this while loop where we're checking, for some convergence. We want the norm of that residual to be, less than some tolerance. And inside here, we're just going to do kind of the stuff you would expect, right? Newton step, we're going to evaluate the Jacobian of that residual thing. take a Newton step, and then we're gonna do a line search. And this is our MIHO that we already saw. Some new little details in here that we're gonna talk about probably next time because we're out of time, but you can do our MIHO on this guy, right? So that's same stuff you've already seen pretty much. And then we're gonna kind of just iterate this a little bit. So let's do, right, so we're gonna set this equal to 1, solve it, take a Newton step, right? So to be clear, right, what I just did was solve the interior point relaxed KKT conditions to like residual goes to 0, right? Or 10 to the minus 10, or whatever, right? So this took several Newton iterations, probably 4 or 5, right? And what I got out is a relaxed solution. So if I check that on the original KKT residual, everything's 0 except that complementarity, right? Because that's the thing we relaxed. So that's because rho equals 1, that's super slacked out and relaxed. And so it didn't go to 0. So now what we can do is we can start driving this guy down. Oh, also I want to plot this. So kind of intuitively, right, by relaxing that barrier out, we're sort of off the boundary, right? We're gonna have to keep driving that road down to get closer and closer to the boundary. So let's take a look at that. So let's put this at like, 0.1 now. So E minus 1, and we're gonna warm start from our previous solution and solve it again. So a couple Newton iterations. KKT residual now is 0.01, right? So we're getting closer to satisfying the original KKT conditions. And down here, we got closer to the boundary, right? And so this is, by the way, this solution curve, as you crank rho down, this has a name. It's called the central path in the theory of interior point methods. Fun fact. So we'll keep doing this and sort of intuitively, right? We're going to get closer and closer. So now it's 0.01, and we're like getting closer, right? And I can keep doing this. In fact, I can crank this a lot more aggressively. So if I kind of go down to, I don't know, 10 to the minus 4, now this is like 1e minus 4 down here. And we're like getting really close. And I can be really aggressive and crank this much faster than I'm doing. So we'll go down to like 1e minus 8. And now we're basically right on there. So these are the original KKT, not the relaxed ones. And now that complementary slackness thing is satisfied to 1e minus 8, right? And that's as far as I care, right? Like I don't care about going farther than that. And now we're like right on the boundary and like life is good. Cool? Okay, yeah. So in general, like you just come up with some schedule for this and crank it. And you don't have to like, basically like you would like to crank it as fast as possible to get to the answer as fast as possible. Sometimes that might go off the rails. Like there might be ill conditioning numerical problems with that, but for a convex problem like this, it's benign. You can actually crank it super aggressively. In fact, here I probably could have gone right to 1e minus 8 and just solved it once. I'm just showing you this central path idea. In general, you want to crank it down, and there are good ways of cranking it that basically look at the constraint violation and like look at the residuals, and they decide on a row that's like sort of scaled to sort of account for how close you are to the solution in general.
It's like maybe like on the first iteration, what would happen if your row was like super small?
I mean, in general, if it's super small, remember what that landscape looks like then. It starts to look like the brick wall, right? So the problem with that is if you're somewhere in the interior and you set it crazy low, your gradients are going to go to 0. And now you won't like have any gradient information to push you in the right direction.
It's like an exploration versus expectation.
Kind of, yeah, if you want to think about it that. I mean, it's basically like kind of a conditioning. You need the gradient information there in the beginning, but then as you get closer, you can kind of crank it, right? Okay, that's it, guys. See you next time for more fun. Thanks.